Hello everyone, this is Engineer Selassie from the Academy and Brain Boosters, and today we are going to see chapter 20, which is paging, and this is smaller tables. So paging, this is linear tables. We usually have one page table for every process in the system, and assume that 32 bits address space with 4 kilobyte page and 4 byte page table. So as you can see, we have the entries. So each entry will be 4 bytes. Okay, so this is a page table for process A. And as you can see in the physical address, this is page 0, page 1, page 2, until page N, and we're going to have 4 kilobytes, okay, in the physical memory. So as you can see, the address space is 4 kilobyte pages. So if you calculate this page table size, then we're going to have to the power of 32 over 212, this times 4 bytes. This is going to give us 4 megabytes of space. Page tables are too big and just consume too much memory. As you can see, we need 4 megabytes. Paging a smaller table by using bigger space. So to alleviate that problem, instead of making the paging tree 4, we can make by bigger pages, okay? Instead of 4 kilobytes, we can make 16 kilobytes, okay? Then in this case, page tables are too big and thus consume too much memory. Assume that 32 byte address space with 16 kilobyte pages. Now we can make 16 kilobyte pages and 4 bytes of page table entry. Then as you can see, we have in the page table process A, we have 4 bytes, but in the physical memory, we have 16 kilobytes. So if you check this to the power of 32 over to the power of 16 times 4 bytes, we're going to have 1 megabyte per page table. So we dramatically reduce the size, but the issue is big page lead to internal fragmentation. That is the idea, because internal fragmentation means OS will assign more memory than the requested, so that the internal memory will be, we call it internal fragmentation. So let's see, for example on this problem, single page table for the entries address space of the process. Let's assume we have 16 kilobyte address space with 1 kilobyte page, okay? So we have 16, as you can see, okay, 16 kilobyte address space. So this is a virtual address and we have the physical memory. So if you see, 0 is mapped to 9, 4 is mapped into 15, 13 is mapped into 3, 14 is mapped into 23. So if you see this in the page table for 16 kilobyte address space, this is address space, but we have to include one column here to show the virtual address space. For example, 0, we have 10, okay, and this frame number, okay, physical frame number, page frame number. 10 is it is for 0, as you can see. And if you see 15, we have 4, okay, 4 is for 15. If you see 3, 3 is for 13, and if you see 23 is for 14. So the virtual memory is mapped into the physical memory. and the valid bit, the protection bit, the present bit, the dirty bit, all are here, all are the bytes. The issue in the entry is, as you can see, only a few row has entered. However, most of it is empty, which is a waste of memory in this situation. Most of the page table are full of invalid entry. As you can see in this area, again in this area, we don't have nothing. So this is the waste of memory with invalid entries. So this is all invalid. As you can see, this is the invalid entries. So the problem is most of the page table is unused, full of invalid entries. So how to resolve this problem? To alleviate this problem, we have the so-called hybrid approach. This is paging and segmentation. So we will use paging and segmentation. Let's see how can we solve this problem of invalid entry in order to reduce the memory overhead of page table. Okay, because this is all the overhead invalid entries. So using base not to point to the segment itself, but rather to hold the physical address of the page table of that segment. So in our previous chapter we have seen base and bound system of address translation, but in this case, in the hybrid approach, what we are going to do, the base not to point to the segment itself, but rather to hold the physical address of the page table of that segment. So this is a critical point. The bounds register is used to indicate the end of the page table. So the bound register also pointing to the end of the page table, not the end of the virtual address. So this is the idea. So simple example of hybrid approach. Let's say each process has three page tables associated with it. For example, we have code, we have stack, and we have. Okay, so the code, the stack, and the heap, we have three page tables. And when process is running, the base register for each of the segment contains the physical address of a linear page table for that segment. So when a process is running, the base register for each of the segments contains the physical address of a linear page table for that segment. This is the idea. So if you see here now, we have the 32-bit address space. And the difference here is, if you see, we have a segment number here. Okay, segment number SN is included here, and we have the VPN, and we have the offset here. So 32-bit virtual address space with 40 pages. Okay, so what we are going to do, if it is 00, this is unused space. Okay, if the SN, the segment number 00, this is unused segment. If it is 01, it is a code segment, and if it is 10, it is a heap. Okay, and if it is 11, it is a stack. So this is the general form of the simple hybrid approach. So what is TLB miss on the hybrid approach now? What is TLB miss? So the hardware get to physical address from page table. The hardware uses the segment bits, to determine which base and bound pair to use. The hardware then takes the physical address therein and combines it with the VPN as follows to form the address of the page table entry. So as you can see in our code, we have the SN, okay, the segment number, So through the segment number we have the virtual address, and with segment mask we're gonna mask it by segment same shift. And second, once we have the VPN, the virtual address, and in the virtual address also we will make VPN mask and again VPN shift. And thirdly, as you can see, address of the PTE is equal to base of the segment, okay, the segment number plus the size of the PTE. So this is page table entry, okay, the page table entry. So problem of hybrid approach. Hybrid approach is not without problem. It has a lot of problem. For example, if you have a large but sparsely used heap, you can still end up with a lot of page table waste. Again, causing external fragmentation to arise. Again, because the page table can be arbitrary in size. These are some of the problems. So let's see the second approach. Now, instead of single, let's see multi-level page table. Multi-level page table turns the linear page table into some kind of something like a tree. Okay, so chop up the page table into page sized unit. Okay, so if an entire page of the page table entry is invalid, don't allocate that page of the page table at all. And to track whether a page of the page table is valid, use a new structure called page dictionary. So what this page dictionary will do, it will check the entries, the page table entries, and it will see if there is valid or invalid. If it is invalid, then the page dictionary will reject it. Okay, it will not include it in the page dictionary. Let's see an example. This is multi-level page table. We have the page directory here. Let's say we have here linear page table, and we have here the page table base register. Okay, this is a page table base register, and this is 201. And as you can see, we have the valid bit and the protection bit, and we have the physical frame number, the page frame number. So if you see the page, the frame number 201, we have something, but page frame number 202, it is nothing. And page frame number 203, we have some data. So what the page dictionary does is it will include the valid bit and the page frame number. For example, the page frame number 201 and page number 202, 203 are valid, but page number 202 is invalid, so it will remove it. So you will find this data in the page dictionary. Okay, then what it does will be, it will show you the page table, okay, like the linear page table, like this, the valid, the protection bit, and the page frame number will be shown like this. So the invalid ones will be rejected. Okay, so the page table not allocated, and page 2 of PT not allocated. So as you can see, we have page table 201, and we have here also 11 here page. So we have also the page frame number. So in this way, the page dictionary concept will remove the invalid parts from our page linear page table. So multi-level page table, page dictionary entries. The page dictionary contains one entry per page of the page table. Okay, as you can see, one entry per page of page table. So we have only one entry. So that's what it means. It consists of the number of page dictionary entries, PDEs. It consists of the number of, as you can see, we have the number of entries. So 201, 203, like something like that. So page directory entries. PD has a valid bit and a page frame number. So as you can see, we have the valid bit and page frame number. So what is the advantage and disadvantage of multi-level page table? The advantage will be only allocates page table space in proportion to the amount of address space you are using. Again, the operating system can grab the next free page when it needs to allocate or grow a page table. These are the two advantages. The disadvantage will be multi-level table is a small example of a time space trade-off and complexity. So these are the two disadvantages we have. Multi-level page table, the level of indirection. So a multi-level structure can adjust level of indirection through use of the page dictionary. So as we have here, we see that by the use of page dictionary, we can remove the invalid areas. So indirection place page table pages wherever we would like in the physical memory. So a detailed multi-level example. Now let's see an example to understand what we have been discussing till now. To understand the idea behind multi-level page table better, let's do an example. Okay, let's say we have 16 kilobyte address space with 64 byte pages, okay? So this is address space. So as you can see, we have code, we have heap, we have stack, okay? And the flag and the details, the address space is 16 kilobyte and the page size is 64 kilobytes. And the virtual address we have 14 bits. And the VPN we have 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. And the offset we have 6 bits. 1, 2, 3, 4, 5, 6. And page table entry we have to the power of 8. 256 page table entries is available. So this is the detail of our example. Now a detailed page directory index. The page directory needs one entry per page of the page table. So as per our example, it has 16 entries, okay? And the page directory entry is invalid. When the page directory is invalid, then it raises an exception. The access is invalid. The idea is this one. The page directory index is here, okay? The page directory index. We divide the VPN into 2 and we have this 14 byte virtual address and we have 4 bits. So a detailed example, page table index. The PDE, okay, the page directory index is valid. If the page directory index is valid, we have more work to do. Okay, what we are going to do, if it is invalid here, then raise an exception. If the directory index, okay, is valid, to fetch the page table entry, okay, page table entry from the page of the page table pointed to by the page directory entry, and this page table index Okay, page table index can then be used to index into the page table itself. So as you can see, we have VPN and we have page directory index, and we have the page table index. It is divided into this. To fetch the page table entry PT from the page of the page table pointed to by this page directory entry. This is an example, just page directory. We have page frame number. This one is page of the page table, and we have the physical page frame number 100 in the page frame number 11 page of PT. And let's see an example. Let's see a real example. Let's say a detailed multi-level example. Translation of virtual address 0x3F80 hexadecimal address. This is a virtual address. So let's see how the multi-level example, the multi-level translation works. Okay. So step 1, convert the virtual address, this 0x3F80 to binary. So if we change into binary, we have 11111110000000. This is a binary form of F80 to binary from hexadecimal, because this is the address of the virtual memory. Now the second step, as per detailed multi-level example, now page directory index extracts the VPN. Okay, so to extract the VPN, this is a structure. As you can see, to extract the VPN, we have to 1, 2, 3, 4, 5, 6. So let's 1, 2, 3, 4, 5, 6. So 0, 1, 1 will be the VPN. It starts from this location. Okay, so the VPN is this one. Second, binary. Second is VPN. Now the third one is offset. As you can see, the offset is the beginning 6 bytes. 1, 2, 3, 5, 6. So 1, 0, 0, 0, 0, 0, 0. So this is the offset. Okay, this is the offset. Step 4. Again, as per the detailed multi-level page dictionary index, extract the page directory index. As you can see, the page directory index is half of the VPN. Okay, half of the VPN. So what we are going to do, page directory index is equal to 1111, because half of it. We obtain a valid. Now once we get the page directory index, here the page directory index, let's assume now we find the page frame number 101. Okay, let's assume that. So let's assume we obtain a valid page frame number 101. Okay, now step 5, as per detailed multi-level index into the page of the page table. So what we are going to do, index into the page of page table. Okay, the page of page table at page frame number 101, and this will be this part. Okay, this part will be, let me show you, page table index. Okay, the rest will be page table index. So this will be page table index 1110. Okay, 11. So if we go here, page table. Okay, page of page table, and the page frame number 101. Then if we find, let's say at this location 101 location, we found 55. Okay, we found 55. So at that location 101, this is 1110, we obtain a valid page frame number 55. This 55 is equal to, in hexadecimal, 0x37. So step 6, convert this into binary. So when we convert this into binary, 11011111, and add offset after shifting to left 6 byte to obtain the physical address. So as you can see, 110111, 110111, then we will add the offset 000000. The offset is this one. Then if you change this binary into hexadecimal place, you will find 0x1DC0. This is the hexa, the physical address. This is the virtual address 0x3F80, but the physical address will be 0x1DC0. So in general, the multi-level page, so the multi-level system, the translation system works like this, okay? So yeah, multi-level page table, this is how it translates the virtual address. So if we need more than 2 levels, so in some cases a deeper tree is possible. For example, let's see, this is offset, this is a VPN, we have 30 bits, and as you can see, virtual address, we have 30 bits, page size 512 bit, VPN, we have 21 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 18, 19, 20, 21, and the offset will be 9 bits. More than 2 level page table index, even what we can do, in some cases a deeper tree is possible. So instead of this, we can also, as we have seen this page table index and page directory index, and we have the VPN and we have the offset as well. So in this situation, in deeper tree, virtual address we have 30, and page size we have 512 bytes, VPN 21 bytes, offset 9 bytes, and page entry per page we're gonna have 1 to 8 page table entry. Okay, page table entry. More than 2 level again page directory. If our page directory has to the power of 14 entries, it spawns not 1 page but 128. And to remedy this problem, we build a further level of the tree by splitting the page directory itself into the multiple page of the page directory. So we can go deeper as well. As you can see, page directory index 1, page directory index 0, page table index. So we have to offset as well. So multi-level page table control flow. This is the control flow. So what it does is we have the VPN. We always start with the VPN. So we have the virtual address and we have the VPN mask. Okay, we have the VPN mask, then the shift, then success, then TLB. Okay, entry. We will check the TLB entry. If the TLB lookup of the VPN, if it is success, then TLB hit. Okay, if you find once we check in the TLB entry, then if the VPN is there, then this is TLB hit. If then we will check the protection bits, security issues, and we will check the offset again, virtual address and offset mask. And once we get the offset, then the TLB entry, okay, the TLB entry, and we will attach it with the page frame number, okay, the page frame number in the physical address, and again we will shift and the offset. Then in the register access memory in the physical address, and through this physical address we will get the page frame number. Then the register will go in the physical address. But otherwise, there is an exception, protection fault. Okay, perform the full level lookup. So if this is for KLB hit, so as you can see, extract the virtual page number, then number to check if the KLB hold the translation for this VPN here in the lookup, and 5 up to 8 extract the page number from the relevant KLB entry and form the desired physical address and access memory. But if it is not here, what we are going to do, the page directory index, okay, the page directory index is equal to VPN, and we have the page directory mask. Again, we will do the page directory mask, and we will shift the page directory shift, and we have also page directory entry address, and we have also page directory base register plus page directory index times size of the page directory entry, and at the end of the day we have page directory entry is equal to access memory, the page directory address here. So if page directory entry is valid, this false, then there is exception. This is segmentation fault. Page directory entry is valid. Now fetch page table entry from the page table. So as you can see, extract the page directory index and starting get page directory entry, and 15 up to 17 check page directory entry valid flags. If valid flag is true, fetch page table entry from the page table. Next, as you can see, we have page table index, and we have the VPN, and we have page table mask and page table shift, and the page table entry address is equal to page directory entry and the page frame number shift and plus page table index and size of page table entry, and the page table entry is equal to access. Now we can access memory in the page table entry address. Then if the page table entry is false, then there is exception. This is segmentation fault. If again the protection, the page table entry protection bit is false, then protection fault. Then the TLB, okay, insert. We have the VPN, we have the page table entry, page frame number, and the page table entry protection bit will be there, and then retry the instructions. So in the nutshell, it's a little bit long, the code is long, but this is how each line of code is working in the multi-level page table control flow. I hope it's simple, and I advise you to see it again. Then inverted page table, we have inverted page table. This is another method, keeping a single page table that has an entry for each physical page of the system, and the entry tells us which process is using this page and which virtual page of that process maps to that physical page. And our PC uses inverted page tables. So in the nutshell, that was the idea. So we have seen inverted page tables, and we have seen the translation processes, all the TLBs, and we have seen the control flows, each line of code, and more than 2-level page directories, and page table indexes, and more than 2 levels if there are. And we have seen detailed example how the multi-level table works. Okay. As we have seen the virtual address and the physical address translation, and we will use detailed multi-level examples. This is the example. the disadvantage and advantage of material page table also discussed, page table entries, and we have seen the concept of the page directory, because to alleviate the overhead and the unused space, how to remove that, we use the page directory, and only the valid bit and the page frame number is included in the page directory. And multi-level, we have seen that, and problem of hybrid approaches, and KLBBs on hybrid approaches, simple example of hybrid approaches, and paging and segmentation, and we have seen invalid entries. The problem, we have seen this problem. So a small table using bigger pages also, we have seen this will give us the smaller page, 1 megabyte, but the problem is internal fragmentation. So the page size, whenever we are increasing the page size, then internal fragmentation is expected. But this one was good because the page size and the virtual address size is the same. But the issue is that we need huge amount of memory. The page table too big and consume too much memory. So in a nutshell, that was chapter 20, paging smaller tables. I hope this video was helpful, and I advise you to go to the textbook and read deep dive in the book, and you will get an idea. But for now, that was it. Thank you so much, and we will meet in the next video. Bye bye.